talking about uniform circular motion. So uniform circular motion is when an object moves in a perfect circle or moves in a circle at a constant speed. Now don't forget though, even though it's moving at a constant speed, yes, it's accelerating because it's continuously changing directions. For an object to move in a circle, it must continue to change its direction to turn into a circle. Then I left off with this last portion over here. If an object moves, and every time it always starts over here at 0 degrees and it moves upward, and that means we call that counterclockwise. That is what we call the positive direction. If it starts at 0 degrees and goes downward, that is what we call clockwise or in the negative direction. Then we talked about this last equation, which should not have been on the quiz, which is angular displacement. Now, angular displacement, even though it sounds like angle, we do not use a degree. We actually use what we call rads here in physics. And we like to talk about rads because rads can be correlated into a straight line. We can figure out what that radius is of that circle, and we can go around the circumference. Even though that's a circle, we can convert that circle arc into a straight distance because we know what the radius is. And so we call this angular displacement, and the SI unit, one more time, is a rad, not a theta or a degree. Okay, so I'm going to come over here and look at this practice problem. So this practice problem says that there's this, kid, little Johnny, and so little Johnny is at the playground, and little Johnny's on the merry-go-round. The merry-go-round has a radius of 1.7 meters. Little Johnny moves at an angular displacement of a theta of 100.48 rads. Now, just a quick reminder. Remember, if this is a full circle, a half of a circle, which would be the top part over here, is 3.14 rads. A full circle would be 6.28 rads. Little Johnny here rotated 100.48 rads. That would be 100.48 divided by 6.28. That means that little Johnny rotated 16.025 rotations. Okay? Remember, that's what we were doing before I left out of town. So little Johnny rotated a little bit over 16 times. He rotated in a circle or on the merry-go-round. It says here, what is little Johnny's arc length? Question mark S. If we were to get a piece of string and little Johnny rotated 16 times and we got that string around that circumference of the merry-go-round, how long would that string be in a distance or the arc length? Well, theta equals S over R. They gave us the theta of 100.48 rads. They also gave us the S of my unknown, but the radius they gave us of 1.7 meters. I can see that this is being divided, so if I multiply by 1.7 meters, cancel, multiply by 1.7 meters. Now in this situation, I can go ahead and find out that little Johnny's arc length, or the distance, because if I had a piece of string and wrapped it around the merry-go-round 16.025 times, then it would be a distance of 170.8, I'm going to round it up, 2 meters. Would be how much that string would have wrapped around the playground or the merry-go-round into a straight line string of 170 meters in distance. Now it says here that we've got a new planet that was discovered orbiting the moon of Earth. If someone at the equator of this planet travels an arc length, S, of 63.69 meters, let me scroll in a little bit, And the angular displacement, or theta, is 6.28 rads. What is the radius of this planet? Question mark R. Well, theta equals S over R. They gave us the theta of 6.28 rads. The S was 63.69 meters, and I'm looking for the R as my unknown. So for this situation, you would go ahead and you would need to solve for the R, right? Multiply one side by 63.69, multiply the other side as well, and you can solve for the R, or the radius of this planet. If they were to ask you to find the diameter, then you would just get that radius, multiply it by 2, right? So you can figure this stuff out. Now, before we go on to the new information, I'm going to pause for a moment, and I am going to pull out my highlighter, because just like I've done in the past, every time we have an equation that is not on the formula chart, I like to highlight it. Alrighty, but I'm also going to go ahead and highlight over here on the side as well. All right, so here's my highlighted section. We have formulas that are not on the formula chart, and it comes to a memorization. Not only that, we use it first semester, and we use this information second semester as well. Now, this variable is a capital T. We have not had a capital T yet, and this is actually a lowercase f. We also have not had a lowercase f. A capital T stands for period, and a lowercase f stands for frequency. All right. Now, period's definition is, I write really big, so I'm going to go ahead and write up here first. The time it takes for one full revolution or rotation or turn, whatever word you want to use. The book uses the word revolution, rotation. The time it takes for one full cycle. What's the time for a cycle for a year? 365 days. That's the period of a year. 365 days, period. What's the period of a month? 30 days, 31 days, 32 days, 30 days, 30 days. What's the period of a week? 7 days. Takes 1 week. For one cycle of 1 week, 7 days, and then we start all over again. Sunday, Monday, Tuesday, get the week going, or unless you start your week off on Monday. Think of it that way. Monday, 7 days, it comes back around again. One full cycle. Frequency's definition is the number of revolutions or rotations or turns per second. Frequency, how frequent? Now, frequency is measured in hertz. And the great thing about these two equations is that they are inverse of each other, meaning they are opposite. Capital T, one more time, stands for period, which is in seconds. Lowercase f is frequency, which is in hertz, Hz. And the equation that is memorized is T equals 1 over F. And they are opposite of each other. Frequency is F equals 1 over T. They're opposite of each other. Now, the problem, though, comes here in the fact that when we start to do this, unfortunately, they don't give us period, and they don't even give us frequency. They actually give us the definition or the information. So for an example, this is what I truly used. I'm going to come over here and star this. I figure out the period first by solving it as period is the total time over the total turns. The amount of time it takes for all the turns to occur. That is what period is. Because the definition for period is how much time it takes for one full revolution. Okay, so just like all other equations, once I get through writing the equations, then we practice the equations. So let's practice. Number one here is pretty easy cheesy. So we got 2. A Ferris wheel that Carlos has always wanted to ride but has been a little too scared to get on rotates 5 times in 5 seconds. What is the period? Well, they did not give us frequency. So we're going to use the definition of period is, what did we say on the previous page? The amount of time over the turns. Or how much time did it take? A total of 5 seconds. How many turns? 5 turns total. The period is 1 second. Now that we do have the period, now we can solve for frequency. And frequency's definition is the number of revolutions per second. Or frequency is 1 over t. For this situation, it will be 1 over 1, which so happens to be 1 hertz. I don't like this equation or this practice problem, so we have another one to try. The next one. Now, this Ferris wheel is a haunted Ferris wheel. It's even faster. It says here that Samuel got on this ride, and this ride over here actually rotates 20 times in 10 seconds. So again, they did not give us frequency, so we're going to use the definition of time over turns, or how much time total. This was 10 seconds. The amount of turns was 20 turns, or for this situation, it would end up being 0.5 seconds. And again, that would be our period. Frequency, now that we have the period equation, frequency equals 1 over period, or 1 over 0.5, which comes out to 2 hertz. Again, those are memorized equations. Unfortunately, they do not give you period or frequency. It kind of comes out to using the definition. And that's the reason why I like the amount of the total time divided by turns. I like that equation. Now, the next portion over here is going to give you a lot of definitions, and then I'll pause and I'll explain what they're trying to say. So before I go any further, I know that this question always ends up either a semester exam, quiz, test question. So I always like to highlight this one. It's an easy, cheesy one. If you miss it, it's only one question on the whole test. Let me go ahead and start filling in the blanks, and then I'll explain what they're trying to say here. It says, since it's difficult to describe the motion of an object moving in a circle, it definitely is hard. Using terms of what we used last unit of linear equations, we use terms in angles instead. But instead of using the angles in degrees, because we don't use degrees, we're actually going to use the length of the radius. And that's what we started this unit off. with our paper plate of figuring out the length of the radius. We cut that piece of string, we wrapped it around the circumference of our circle, and we found out that this right here was 1 rad. Now, when we did that, we used our protractor, and I personally found that 1 rad here for me was 58 degrees. And I said, hey, you know what? The word of the day is perfection. Well, if we were perfect, 1 rad truly actually is 57.3 degrees. Every single rad 1, 2, and 3, should have came out at 57.3 degrees. 56, that's pretty awesome. If you got even 55 or 56, 57, 58, all of those are great degrees. Those are really close within the range. But because we do not measure in angles to talk about linear straight lines, we do not use degrees, we use radians. So the majority of your time, your calculator should be in rads. Now, circular angular speed has a definition of the rate at which an object rotates about the axis. It says here that the speed and direction of an object moving in a circle, because we're talking about circles, is called tangential velocity. And this is because the direction is always changing to the circle. For an object to rotate in a circle, at every given point in that circle, it has to change directions, change directions, change directions. It says here, objects moving in a uniform circular motion will have a constant uniform speed. Correct. We said that a couple of pages back. But this does not mean that they have a constant velocity. No. And the reason why is because we can recall that speed is a scalar quantity and velocity is a vector quantity, meaning that it has magnitude and direction. So while it says the magnitude of the velocity vector may be constant, and the direction velocity vector is always changing, we call this tangential. Now, there's a good chance that you've talked about this in math class or geometry class, and I hope you did. I don't know. The definition of that tangential line is the tangent line is a line that touches the circle. So here's my circle, and a tangent line, touches the circle, but does not intersect through the circle. There we go. Let me redraw that. It touches the outside circumference of the circle, but does not intersect through the circle. So all of that whole paragraph is trying to tell you is that this was, it was over there, some kind of laptop charger. I disconnected it, and it's got this little box that's attached to this rope, okay? Now, if I was to start swinging this, no problem, Miss Munson, go ahead and swing it. Because what would happen if that box was to release and detach then it would fly off. And depending on if it released here, it would fly off that way. If it released here, it would fly off this way. Now what if I'm to turn it this way? Now that's becoming a little worrying because now it can fly off, and if for some reason at this location, at here, if it was to break off, it would fly this way. Or if it was to break off at this spot, it would fly that way. That's a little worrying, Miss Munson. I get you. That's called a tangent line. So all of this whole paragraph is trying to say is that if an object's moving in a circle, and if it's to accidentally break off or lose control of its circle, it would fly off. What's the velocity it would fly off at? Let's turn the page. Maybe this will make a little bit of sense. Most of us have probably seen car racing, right? So we've got cars on the track. The cars are racing around. What if this car was to lose control? What if a tire was to break off or a piece of the car was to break off? Since it's in the midst of this curve, it would fly off in what we call a straight tangent line. What is the velocity or the speed it would fly off and hit everybody who's like watching? That's what we're coming down to. That's what the conclusion is. Pretty easy cheesy. So over here it says, to summarize everything that it was saying on the previous page, an object moving in a uniform circular motion is moving around the perimeter of the circle with a constant speed. And the velocity is continuously changing at every single point or location. Why? Because the changing is direction. The direction is always going to be located tangent to the circle. Tangent to the circle, which means a straight line, which is a new straight line because of the new direction at every point. So for an example, if this was a little circle over here and this little, I don't know, golf ball was shot into the circle and it was to rotate throughout the circle, but at this one point right here, the circle was removed, it would shoot off in a, what we would call a tangent straight line. Well, what's the velocity this ball would shoot off? Well, kind of like kinematic equations. When we did the kinematic equations over here, we asked ourselves, was distance ever used? Was T ever used? Was VR or VF given to us? Well, unfortunately, we do not have a flow chart, but we have multiple equations that we could use. These three equations are on the formula chart. You do not have to memorize them. You just have to figure out which one you're going to use. They all mean the same thing. Just like whenever we went through the A equals VF minus VI over T. Or you can use A equals VF squared minus VI squared over 2D. You could still use both of those and still figure out A for acceleration. Over here, you can use any one of these to figure out the same thing. Tangent velocity, again, means how fast it's going to shoot off if it was to break loose, is a traditional equation of 2 pi r, oh, that looks familiar, over capital T. That's why we talked about period in the beginning, capital T. Or you can use omega, which looks like a W, equals theta over lowercase t, which stands for time. Or v sub t, tangent velocity, equals lowercase r, radius, times omega, That is an omega Greek symbol. Some students earlier today kind of looked at me a little crazy. This right here, this little weird W is actually an omega. Some of you are familiar and have seen an omega look like this. That's actually a Greek capital omega. This is a Greek lowercase omega, kind of like capital A, lowercase a, capital B, lowercase b. This is a capital omega. This is a lowercase omega, just in case if somebody was confused. Alrighty, so tangent velocity. Again, if we want to figure out how fast this little car was to lose control and ram into the people, what's the velocity they would hit the people? Tangent velocity and because it's velocity, just like if it was moving in a straight line, it's still meters per second. 2 pi r. R stands for radius. Radius is distance, so that's meters. Capital T, we said earlier today, which is period. And earlier today, we used the SI unit for period in seconds. Or you can use the omega equation, which stands for angular speed. Remember at the beginning of school, we started off with speed and velocity. Speed is d over t. Velocity is d over t. They were both used interchangeable. But angular speed, even though it's really similar to tangent velocity, it actually does have a different SI unit. It's a rad per second. But remember, rad is the same thing as distance in meters. So they're kind of the same, tomato, tomato. Now we did this one already. This symbol right here, we understand and we know it's a theta. But when we're talking about circles, then this theta stands for angular displacement. That's an equation that we had a couple of pages back, which has a unit of a rad. Lowercase t stands for time. How much time did it occur? Which is in seconds. And then our last equation, again, whichever equation's easier for you to use, that's the one you're going to pick. They all come out to the same thing. Tangent velocity which is meters per second, could be radius, which is in meters, times angular speed. Which is rad per second. Hopefully not too bad. So we practiced those, or we went through those. Now let's practice. When you're ready, turn the page. We're going to practice those practice problems. And then we've got one more equation to go through today. And like I said, later on this evening, I will go through and tweak and change whatever we were behind on, whatever I missed. All righty. So here we go. We've got a car that's driving around this circle. It says here that the distance from the center of the circle is actually 5 meters. It completes 3 laps, which is the amount of turns, and it took 60 seconds, the total time. So that's the information it gave me. First question is the radius. Well, from the center of the circle out, is the radius, which so happens to be 5 meters. The period, remember period is 1 over F, or since they did not give us frequency, then period is going to be the amount of time divided by turns, which is the definition, or 60 seconds. If they gave us 1 minute, we would call it 60 seconds, divided by 3, so that way we can figure out that our period would be 20 seconds. That's how much time it takes for one full rotation. In tangent velocity, you've got 3 equations you can use. Equation 1, equation 2, equation 3. They all get you the same answer, just like our flow chart for kinematic equations. But since I have radius and period, equation 1 is like our easiest go-to equation. So tangent velocity equals 2 pi r over period. Or 2 pi, r is 5 meters, over, we calculated the period of 20 seconds, equals your tangent velocity. Meaning if this car was to lose control going around this track, it would shoot off and hit somebody that's watching about 1.57 meters per second. All right, let's practice this again. Now we've got a motorcycle, again, going around a circular track, and it goes from 20 meters across the track. Hopefully you can tell or determine that 20 meters across is actually the diameter. 10 meters now is the radius, not 20. It completes 5 laps, which is the number of turns, and it took 60 seconds, the total time. The first question is, what's the radius, which is 10 meters? The period, which, yes, is 1 over F, but they did not give us frequency, so period would be the amount of time divided by turns, or 60 divided by 5, which comes out to, double check my math, 12 seconds. That should be the period. The tangent velocity. Now remember, you've got 3 equations over here that you can use, but our number one go-to, or our easy one, is the 2 pi r over period, which is great for us because that's the information we have. So tangent velocity, which is 2 pi r over capital T, or 2 pi, we got r of 10, not 20, and our period was 12 seconds. For this situation, if this motorcycle was to fly off the track and hit somebody on the side, it would fly off at 5.2 meters per second. It actually is moving faster than the car. Almost 5 times faster. All right, we're going to practice 2 more practice problems and then we'll turn the page. The next one, number 3. Number 3 says that there's a kid at the ice cream parlor that sits on a stool that spins. Okay. Now, the child turns around counterclockwise, which is positive direction, and the kid's feet displaces 8 rads. Oh, rads. We talked about rads. Rads is theta. Remember, this is 1 rad, 2 rads, 3 rads. A full circle is 6.28 rads. And the kid went, a full circle is 6.28 rads. The kid went 8 rads. So the kid went a little bit further than one full circle and came to a stop. It took a total time of 6.3 seconds to come to a stop. Determine the angular speed, or what's the omega? Again, omega and tangent velocity are like tomato, tomato. Now let's see. I've got a theta, I've got the total time, not period, and I'm looking for an omega. There are 3 questions or 3 problems we can use. This one actually has nothing to do with an omega. This one and this one does. This one has tangent velocity and radius, which we do not have. This one has angular displacement and total time, which is what we do have. So let's use that equation. Omega equals theta, or angular displacement, over t. Or 8 divided by 6.3 equals the angular speed of, double check my math, there we go. Alrighty. Now the next problem, it's a good problem to practice and try. So it says here, we've got this Ferris wheel, and from the center of the Ferris wheel, oh, well that means radius, is 37.94 meters. As the Ferris wheel spins, its arc length around the outside perimeter of the circle distance, remember if we had a piece of string, the arc length would measure 29.8 meters, S, arc length. And it took a total time of 50 seconds. Determine, question mark, the omega, or angular speed. All right. I'm not too sure, Miss Munson. That's okay. Remember, we have 3 equations we can use, but just like we did on linear or kinematics, I'm going to go ahead and just write out my variables. I have an R, 37.94. I have an S, 29.8 meters. I have a lowercase t, not capital, of 50 seconds. And I'm looking for the angular speed, or omega. Okay, RST is what I have. Coming over here, equation number 1, it has an R, but it has a capital T, not lowercase. That's not helpful. Equation number 2, omega, okay, that's what I'm looking for. It has a theta, or an angular displacement, and it has a T. I have T, check, but I don't have this omega, theta. This one has a angular speed, check, which is what I'm looking for. I have R, check, but I don't have tangent velocity. And I can't even come over here to find tangent velocity because I don't have period. There's more than one way to skin this cat. Okay, so what we could do is we could come over here and do a 2-step problem. I'm going to come over here and I'm going to go back a couple of pages. I don't remember if you recall, but there's this equation, angular displacement equals S over R. We're going to do this equation first. Theta equals S over R. We're going to solve for the theta, and then we can use equation number 2, which is theta over time. Let's do that. 29.8 over 37.94 that's going to equal my 0.79 rad. I'm going to put theta equals 0.79 rad, not my answer. And I'm going to say part 2 equals omega equals theta, or angular displacement, over over time, not period, or 0.79 over 50 equals 0.016 rad per second. There we go. Not too bad, hopefully easy cheesy. We did have to pull back another equation that we used prior, so that way we can solve for it, okay? Remember, those 3 equations are on the formula chart. They are not highlighted, so you don't have to memorize those. We are going to turn the page, and this is all we did earlier today. All we did was we wrote our last one, our last equation in. So centripetal acceleration. Centripetal acceleration is just like what we talked about prior when it comes to acceleration. An object is speeding up or it's slowing down, but it's changing its velocity. All right. The new word here, though, is centripetal. Some people pronounce this centripetal, which is okay as well, if that's how you pronounce it. I pronounce it as centripetal. Centripetal acceleration. Remember, acceleration had a lowercase a, but we're going to put a little c because that stands for it moving in a circle. Equals velocity. Remember, it was the change in velocity, but here it's tangent velocity squared. Okay? A little different. Divided by r. Or centripetal acceleration, or centripetal, depending on how you pronounce it, which our acceleration was meters per second squared. It's still meters per second squared. Tangent velocity, or tangential velocity, which is meters per second. And lowercase r stands for radius, which is in meters. So again, centripetal, but the acceleration means that an object's either speeding up, slowing down, or changing directions. It says here, is an object moving in a perfect circle at a constant speed accelerating? Absolutely, yes, it's accelerating, even if it's moving at a constant speed. It says, remember that velocity involves not only speed, but also direction, because it's a vector quantity. The direction is constantly changing. So the object is always accelerating. This is what we called centripetal acceleration. Centripetal acceleration is the acceleration of an object moving in a circle. That's it. I told y'all earlier today we would stop that centrifugal acceleration. We will to work on the practice problems when we see each other on Thursday. Then we have a couple of more circular movements, and then we're going to talk about work and power, and that's it. Our notes will be done by Friday. Now that classes are over, now I'll stop, pause, and put up our